answer or ask questions. Um, Arnab, should I start recording? Okay, thanks.
I started it. Yeah, you can begin the
Okay.
talk.
Yeah, welcome guys. So today it's going to be an introduction session to game theory. So we're not going to get into like too many mathematical concepts or like too many complicated things. I'm just going to first go through some interesting problems that we could solve. And then I'm just going to take you through the basic notions and definitions in game theory and end with some theorems, but it's not going to be too heavy. So I hope you guys enjoy. So first, we had put out a question on our Facebook page and on WhatsApp and asked this question about the alpha roll bar, where the fixed population wants to go to the alpha roll bar every Thursday night. But if too many people go, then they won't have much fun because it'll be too crowded. And if too little people, and so under a certain amount, people will have fun if they go to the bar, right? And the constraints were given is that people don't know what the other people's choices are, but they do have a database which tells them how many people have attended since the day it opened. So I think Shreya answered this question correctly in the comments, or had a good direction to where it was going. Until then, does anyone else have any ideas? You can unmute and talk about it. All right. Seeing none, basically the solution that they put up in the comments was that the numbers will fluctuate about the 60% line and eventually even out to a constant of 60% over time, which is a very good solution, I would say. In fact, scientists did research on a slight modification of this problem where the people were only given the attendance for the previous Thursday night. So instead of having a database to the entire attendance, they were only told how many people attended the previous Thursday night. And in that, they found more or less a triangular or a sine curve about the 60% line. And so I think it is a fair assumption to say that if people are given the entire data, so that is the problem. Now I'm going to talk about some more interesting problems. These aren't exactly game theory as such. Mostly they just require a bit of logical thinking. And so, yeah, we're going to go through a couple of them. So first is flag survival. So we would have played variations of this just verbally saying numbers out loud. Hello, am I audible?
Yeah, yeah.
Okay, so we would have played versions of this saying numbers out loud, but for the sake of having a little fun, I guess. Um, there are 21 flags placed in a row, and there are two teams, and each team has to pick one, two, or three flags from the pile. So they can't pick zero flags, and they can't pick more than three. And let's say the team that picks first is team A, and the team that picks second is team B. And so whoever picks the last flag is the winner. So does anyone have any strategies for how either team could win this game? Okay, so what's going to happen is, um, suppose there are four flags left at the end, and it is Team B's turn to pick, right? So if Team B picks one flag, then Team A will pick three flags and win the game. If Team B picks two flags, Team A will pick the remaining two flags and win the game. If Team B picks three flags, Team A will pick the remaining one flag and win the game, right? And so you want to reach a point where there are four flags left at the end of the game, and understand that if there are four flags left, then it's guaranteed that you will win the game, right? So we basically use this backward thinking and say, okay, if I want four flags left at the end, then in the second to last round, I want eight flags to be left at the end. In the third to last round, I want 12 flags to be left at the end. And before that, there have to be 16 flags and 20 flags, right? And so if A has to pick the last flag, they have to make sure that they pick only the first flag. So if team A picks only one flag at their first turn, then no matter how many flags team B picks in any turn, As long as team A brings that number up to a multiple of 4 in their turn, they are going to win this game, right? And so in this game, it's guaranteed that team A will win, right? If team A uses this strategy, there's no possible way that team B can win. If team A hasn't thought of this strategy, then maybe team B can somehow make sure that they get to a multiple of 4 somewhere in the game and they can take the game, of course. But a definite winning strategy only exists for team A in the case that there are 21 flags. Now, what happens when there are 20 flags instead of 21? Using the same backward calculation, can someone tell me which team is guaranteed to be the winner? Okay, so if you look at it, 20 is exactly divisible by 4, right? And so what happens is, no matter how many flags team A picks in its first turn, team B can always bring that up to a multiple of 4. So if there are 20 flags instead of 21, then team B is guaranteed a win. And what's interesting here is that if the total number of flags is a multiple of 4, then team B is guaranteed a win. And if the total number of flags is not a multiple of 4, then team A is guaranteed a win because they can just in their first turn pick up the number of flags that are that's the remainder when it's divided by 4. So that's how flag survival works. Does anyone have any questions about how we arrived at this? All right. Seeing none, I'll move on to the next problem. You guys can unmute and throw out guesses as well. There's no problem. I want this to be interactive. So the second is a little bit interesting. What happens is there are two players who are given, say, 1,000 rupees, and they're put in a casino, and they say, okay, you guys have to play the same games together. So whether you go and play blackjack or poker or whatever, play the same games together. And at the end of the night, whoever makes the most money is the winner, and they get some sort of prize or something, or they get to keep the money, whatever. So just before the last game, so the last game they've decided to play is Russian roulette. And as you can see, player A has more money than player B in this at the end of the previous games. So the way Russian roulette works is you can see in the figure there's sort of a circle where the handler puts the ball through and allows it to rotate, and eventually it lands on one of the squares, which has the numbers 1 to 36. And the numbers marked 0 in green. If the ball lands on those boxes, then the house wins all the money that the players have bet. However, if it lands on any other number, then whoever bets that particular number wins. So for example, since the numbers are 1 to 36, if the return that you get on your bet is directly proportional to the probability that the absolute probability that that number has, right? So if I bet on an even number, half of the numbers are even numbers. So if I bet 100 rupees and I say I bet that this is going to land on an even number, then I'm going to get 200 rupees if it does land on an even number. And if it lands on an odd number, then I lose my money, right? Similarly, if I say this is going to land on a multiple of 3, then if I invest, say, 200 rupees, if I bet 200 rupees and it does land on a multiple of 3, then I get 600 rupees back, right? Because the probability that it lands on a multiple of 3 is 1 by 3, right? And so this is how Russian roulette is played. So can anyone tell me a strategy that player A can use so that they're guaranteed a win in this game? They're already in the lead. Is there any strategy that they can use to maintain this lead definitely and win over player B?
Can you please? Yeah, can you please explain Russian roulette once slowly? Like I didn't get what Russian roulette is in first place.
Okay, so the handler from the casino puts a ball, and the ball like rolls through this circular hole in um, the wooden cutout, and it eventually rotates and rotates and lands on one of the squares. So before the handler puts the ball through, you have to bet on where the ball will land, and depending on how much money you bet, you get returns. And also, depending on how narrow and constrained your bet is, your returns are more likely to be high. So, for example, if I say that the ball is going to land on a red square, then half of the squares are red over here. So, if I bet 100 rupees and say it's going to land on a red square, and if it does land on a red square, then the probability that it lands on red square is half. So I get 100 divided by half, which is 100 into 2. I get a 200 rupee return. If it lands on a black square, of course, I lose the 100 rupees that I bet. Similarly, now if I say, okay, it's going to land on a multiple of 3. So the probability that it will land on a multiple of 3 is 1/3. And say I bet 200 rupees on this. So if it does land on a multiple of 3, then the amount that I get is 200 divided by 1 by 3, which is 200 into 3, which is 600 rupees. But if it doesn't land on a multiple of 3, I lose the 200 rupees. So here, essentially, you're making a trade-off between high returns and high risk, right? If you bet on a very safe sort of, okay, it's going to land on an even number, there's a high probability that it will land, but you'll only get double of your money. If you bet on, say, oh, it's going to land on a multiple of 5, or some people even bet on one single number, which makes it 1 by 36. So if it does land on that single number, they're going to get 36 times the amount that they bet. So that's how Russian roulette works. So is there any strategy? What happens is player A can bet before or after player B. There is no simultaneous here. So one player bets first and the other bets afterwards. So can anyone tell me a strategy? I hope the explanation was okay.
Yeah, now the Russian roulette is clear.
Okay.
If A bets after B, then A just has to match B's bet. For instance, if B bets anything,
Yeah, that's
player
correct.
A just has to bet the exact.
Yeah, exactly. So what happens is if player A bets the exact same sort of bet and puts in the exact same amount, then they are guaranteed this 500 rupee lead over player B, right? Because if the bet doesn't work out, player B will lose whatever money they bet, and player A will still have 500 rupees more than player B. And of course, if they win the bet, then they make the same amount of returns on that, and so player A will still have the 500 rupee lead over player B. And that's how this game works, right? So these two are just examples of, say, logical reasoning. They aren't game theory exactly. They haven't been formalized in that way, but it's just a way for us to figure out what kind of thinking is needed, right, to become a game theorist. Now here, there's an interesting problem called Braess paradox. What happens is in this figure, as you can see, let me just, yeah. So in this figure, the first one, you have a source and a destination, and there are two paths that a person can take from a source to destination. So we'll say that the number of vehicles on the road is m, and the numbers next to each of these edges, so these are nodes, and the lines connecting them are edges, and as you can see here, they're directed. So you can go from S to A, but you can't go from A to S. So the numbers along these edges are the time that it takes to go from S to A to T, etc. So you can see here that it takes m by 50 time to go from S to A, and then another 25 minutes to go from A to T. And here it takes 25 minutes to go from S to B, and m by 50 time to go from B to T, right? So you can see here that if the same number of vehicles choose both the paths, then it will take the same amount of time whether they go through A or they go through B. Now, what the interesting thing happens when you introduce a link between A and B directed along A to B, and you say that the time to go from A to B using this link is negligible, it's zero, right? And so it's almost instantaneous going from A to B. Now, the paradox that arises here is, so you can't go from B to A, so obviously this 25 plus 25 constant time is not possible. What happens is more people will now start using the road, right? For example, here if there were 50 people, then this route would take 26 minutes, this route would take 26 minutes. Now if there are 50 people, this route only takes 2 minutes, right? And so more and more people will start using this particular route. What happens when more and more people start using this particular route, SABT? The people who are using the routes SAT and SBT will obviously be at a disadvantage, right? Because now they have this 25-minute constant time, and as long as this sum is greater than is less than or equal to the time taken here, so as long as m by 25, as long as m by 50 is less than 25, which means as long as m is less than 1250, this route is more advantageous than going up down, right? Either through A or through B. But what happens is, since it is now more advantageous to use this route, instead of using the constant time route, more and more people will start going SABT, right? And so that adds up, and that's what happens. That's what this paradox is, right? So because there is now a short link introduced here, more and more vehicles will start moving here, and this time will actually start exceeding the time if people had just gone this way. But the problem is, if people give up this particular route and go back to using SAT or SBT, then again the number of vehicles using this decreases, and then again the time will become less than any of these two routes, and again there's a paradox, right? And so that's why this is how this paradox comes about, right? Adding extra capacity or adding a new link or adding a new highway actually makes it worse for commuters in terms of time delays than if there was no link added, right? There will be further explanation on this in the subsequent talks when there are topics such as Nash equilibrium, etc., discussed, where they'll explain why exactly, how exactly this is made constant, etc. So these were three of the interesting problems that we looked at today. If anyone has any questions before I move on to the next section.
So, like, okay, I would like to add on this. So, if anyone is still not getting the idea regarding here, just try to substitute some values of m actually. Like, the kind of values you can take is something less than 1250 you can take, maybe 1000 you can take. So, say there are 1000 passengers. So, you do the 1000 by 50, which will be 20 actually. So ideally SAT will cost you 45 minutes, but now if you go to SABT, it will cost you maybe uh like
40
like
minutes.
yeah, 40 minutes, like if they're equally divided. So let's say like the total number of vehicles are 2000 in total. So if they go equally, then it will cost them for 45 minutes in total. But if everyone takes the path of SABT, then the time will now double, because the number of people going through those paths will become 2000. So SA will take 2000 by 50, which is 40 minutes, and B to T will take another 40 minutes. So it will become 80 minutes. So in this way, adding an extra path will actually increase the time. So just people will start acting greedily and will try to take a better path, and in turn they'll make it a very bad path. So in future talks, as she told, we'll have a better look at this particular problem. Yeah, you may continue.
Okay, thank you so much. All right, we come to the next. So this is just a formal definition of game theory. What game theory actually looks like is, first we're building mathematical models. So it won't be the sort of backward reasoning that we did for the previous few problems. We'll have actual tables and actual mathematical models for the game. And we're looking at strategic interactions, which means that people are out to make the best decision for themselves. They're rational decision makers. They want the best outcome for themselves. We can assume them to be selfish and greedy, which means they want the best for themselves, right? And so here it just talks about where this is applied. So obviously it's applied in logic and computer science. It's quite closely related, as we've seen. But it's also employed a lot in economics. And if you guys have watched this movie called A Beautiful Mind, it's the biography or the biopic of a man named John Nash, who won the Nobel Prize in Economics for Nash equilibrium, which is actually an idea in game theory. But game theory applies widely to economics and other fields as well. So that's why it's interesting and important to study this field. So now I'll start talking about some of the formal definitions we use in game theory. First, we're going to define what a strategic form game is. So how do we define a particular game? We use a tuple. You guys would have seen tuples in computer programming or other mathematical concepts that you studied before. It's just a set of objects, and each object can have as many sub-elements as they want. So the first item in this is n, which is the number of players or the set of players. Then you have SI for each player, which means each player has a particular strategy. So this is called a strategy set. So S1 is a strategy set for player 1, S2 is a strategy set for player 2, and so on. So each player has a strategy set which contains whatever strategies they can use in the game to sort of further and get to their objectives, right? And the next term is UI. So UI is a utility function or a payoff function. So it's a mapping from the set of all strategies employed by all the players in the game to a real number for that particular player. So UI for player 1 would be, say, a mapping from S1 cross S2 cross all the way to Sn. Whatever strategies these people use, you have a sort of function for it, which is defined in the question or the problem, and you map it to a particular real number. And ideally, the lower the utility, the worse it is for the person playing the game. So in game theory, basically each player is trying to maximize their utility. If the utilities are all negative numbers, they're trying to go for the greatest negative number, right? So if the possible utilities for a particular player are -1 and -2, the player will want to choose the utility which is -1. Similarly, obviously, if it's 0 and some positive number, the player will choose the positive number. If it's 0 and a negative number, the player will choose 0, and so on. So that's how we define utilities. Does anyone have a question about these definitions?
Will you please explain the utility once again?
Yeah.
Okay. I'm coming to that slide here. So the utility is
Shriya,
basically...
can
Yeah.
you just go back to the first slide?
Okay.
Yeah. So okay. So the thing which I would like to add here is like for strategy sets, you can like consider one particular player and think about that player. Like what can that player do? Like what actions can that player take? So that is basically strategy set of that player. Now, if one particular, so if suppose everyone has decided that they will play one particular strategy or action, interchangeable terms, then each player will get some, you can consider money. Okay. So that is basically a utility function. So it depends on the strategies which each and every player is playing. So yeah, Shreya, you can take over. Yeah, you can add on that.
Okay, thanks a lot. So yeah, utility is basically the value that that player is going to derive out of using that particular his particular strategy. So let's say the strategy set for player 2 is either 0 or 1, right? Let's say the strategy sets for all the players are 0 or 1. We'll come to what these can mean later on. But let's say each player can either choose 0 as the strategy or 1 as the strategy. So the utility for player 1 is basically if player 1 chooses a strategy, say 0, and similarly all the n players have chosen a strategy. So you can see here that this is a unique multiplication, right? S1 cross S2 will be unique for each combination of strategies that each player can take, right? And so the utility for a particular player will be a mapping from this unique combination to a real number. So that's how you get various utilities. I think you'll understand this better when we come to the payoff matrices, and I'll explain exactly where these strategies and utilities come in. Before that, I just want to talk about preferences. So as I spoke about before, these utilities, right? The value that the player is deriving from using a particular strategy. Obviously, if there are a certain set of outcomes, the player will want to have the best outcome for himself. So we can denote this preference relation as an ordered set of the outcomes. So I've written 1, 2 to n here in order, but it can be anything. It can be 2, 1, 3, 5, 6, 4, whatever, till n, right? It's just an ordered set. And what it means that x1 is greater than equal to x2 greater than equal to and so on xn, which means that the player will prefer x1 over x2, x2 over x3 and so on, right? Or at least equal to, right? So x1 strategy gives at least the same value or the same benefit or the same returns as x2, if not more. Similarly, x2 gives at least the same amount of value or benefit or return over x3 and so on, right? And using this, we can see that the preference relation is reflexive. Obviously, x1 is greater than or equal to x1 itself because x1 is equal to x1. So it satisfies the reflexive. It's also transitive because if x1 greater than x2 and x2 greater than equal to x3, then x1 is greater than or equal to x3. This is from the basic relations and functions that we've done earlier. And it's also complete, which means every possible outcome has to be in this preference relation. It has to be in this ordered set. You cannot leave a particular outcome and say it's undefined. You have to order all these outcomes in this preference relation. Coming to the next idea is utilities. So here we're going to denote the entire set of utilities for all the players. If there are n players, it will be an n-dimensional matrix in Rn. I'll show you how it works for 2 players. You can also visualize it for 3 players in various games. Obviously, as humans, we aren't capable of visualizing 4-dimensional space, but you can sort of visualize 4 players and more using various techniques that people use to visualize 4D, 5D, and n-dimensional space. And it's important to know that the utility that any player gets doesn't only depend on their own strategy. It also depends on the strategies that the other players in the game are using, right? And that's why we have n cubed or n raised to 4 or n squared, depending on how many players are playing this game. Coming to the next idea, it's that all players are rational, which is another way to say that all of them are selfish and greedy and will make decisions that are best for them. So nobody is altruistic. Nobody is going to say, okay, I'll sort of lay easy on this particular thing. You can go ahead and take over. Everyone, it's a dog eat dog world. Everyone wants to maximize their own benefit, which means everyone wants to maximize the expected value. Obviously, we're not able to predict the exact outcome of the game, so we just use expected values. So everyone wants to maximize this expected value of their own payoff or their utility that we've looked at before, right? Everyone wants to maximize their own payoff measured in some utility scale. So the utility scale will be defined in the problem as we come to it later, right? So rationality is basically everyone wants to do the thing that's best for them and them only. They don't care about whether or not that decision will positively or negatively affect the other players in the game. And the fifth and final idea is that all these players are intelligent, which means that everyone playing the game is a game theorist. Everyone playing the game knows what the principles of game theory are. They're able to apply them and make the same inferences for the game as any other game theorist around. So if there are 3 players and you make A and B play a game, B and C play a game, and A and C play a game, then the outcomes will be identical because we're assuming all 3 of them are intelligent players who are game theorists, right? And another thing to take note of is that they will take into account what the other players will be doing in order to determine their own optimal response, right? We did discuss here in utilities that the utility depends on everybody's strategy, not just the current player. And so here these players know that, and they take into account the actions of every single other player in the game in order to maximize their utility and determine their optimal response. So I know that these definitions might have been kind of vague, but I'll come to an example problem and hopefully this will sort it out. So I'm from Bangalore.
Yeah,
I found
so before going to that, so I would just like to add a very funny example. Like, consider the grades, okay, which you get. So everyone will obviously sort of say study to get better grades. Like, ideally, if your aim is to get better grades, so you would like to study as long. So no rational guy will assume that they will not study. And they all know that the other guy will also study. So their grades are not only dependent on their own performance but also the performance of others, because I assume that there is relative grading going on. So you can try to relate this game theory thing to the like real world experience, like say grades and all which we get, which is exactly like the things which is playing out, say in a class, is exactly game theory stuff. Yeah, you can continue now. Yeah.
Okay, yeah. Thanks, Arnav. So the example problem here, you guys might have read the slide, but basically I'm from Bangalore. I found this problem relatable somewhat. Obviously, I'm not an IISc, but basically there are two students who are very good friends and they want to spend time with each other. They have two options to spend time. Either they study together in IISc or they can go to MG Road and enjoy. MG Road is a road here in Bangalore where there are a lot of restaurants and pubs and like cinema halls and a lot of entertainment basically. So you can, and shopping and stuff. So what's happening is that exam season is close by, and so ideally both of them want to study, but they're also okay with going to MG Road and sort of letting off the steam and getting rid of the stress. So the thing is, both these friends have to choose their strategies simultaneously and independently, which means they don't know what the other person will choose. They are rational and intelligent, which means that they want the best outcome for themselves, and they are game theorists. They know what all the outcomes could look like. And so here, I hope this is clear. So player one and player two, these are the two players. These are the N that we talked about earlier. So this N, they are the two players here, right? Player one and player two. As you can see, it's a two-dimensional matrix because there are two players. Now there are two strategies, A and B, and these are the strategies here, right? So strategy A is going to choosing IISc and staying back and studying together. Strategy B is going to MG Road, right? And these are the strategies basically. These are SI. So SI would be A comma B. That's how we would represent the set. S1 would be A comma B and S2 would also be A comma B. Then we come to utilities, right? So as you can see here, it's an ordered pair. Basically, we read it as the utility for player one because whoever is on the row gets the first number and whoever is in the columns gets the second number. So the utility for player one in this case would be 10. Utility for player two in this case would also be 10. Here the utilities are the same for both players in each case, but we'll come to a problem where they are different, right? Now what happens here is, as you can see, if both of them choose both of them choose IISc, that's the best option for both of them, right? Because then they'll get to spend time together. They're also going to do well in their exams. And so that's the best option for them. If both of them choose MG Road, that's also still okay. They might do badly in their exams, but at least they're spending time together. They're really good friends, so they're going to enjoy together. The only bad thing that can happen is if both of them choose different options. So if player one chooses to study and player two chooses to go to MG Road or the other way around, both of them now derive zero utility because neither of them are together, right? Both of them aren't together. They're doing different activities and so they get zero utility. I hope the concept of players, strategies and utilities is clear from this example. If it isn't, feel free to unmute and ask.
Could you
Okay.
please explain what's like SI here once again, the strategy part?
Okay, so SI will be S1 and S2, right? Because there are two players here. Now the options for, just give me a minute. So S1 will be A comma B, an unordered set, because player 1 can either choose to go to ISC or to go to MG road. Similarly, S2 will also be A comma B. So that's how the strategy sets are defined. In this case, the strategy sets are the same for both players. In some cases, player 1 will have one particular set of options and player 2 will have another set of options. And so in that case, the strategy sets will be different. But in this case, the strategy sets are the same and the utilities are the same for both players. Is that okay?
Yeah, I got it.
Okay, let's come to the next portion, which is we're going to construct a few payoff matrices and discuss a few problems. So first we come to the prisoner's dilemma, which is a very, very famous problem. Basically, there are two prisoners who are caught by the police and they're put in isolation and they're asked to confess each independently, right? And so they're asked to confess independently and simultaneously, which means they don't know if the other person has confessed or not, right? And this is the prisoner's dilemma. So here we have prisoner 1 and prisoner 2. NC is not confess, C is confess. Again, not confess, confess. So the strategy set for both players is NC comma C. And here what happens is the police tell them that if both of them confess, then both of them will get 2 years in jail, right? If one of them confesses and the other doesn't, then the person who confesses gets only 1 year in jail and the person who doesn't confess gets 10 years in jail, right? And if both of them end up confessing, then both of them get 5 years in jail, right? So obviously looking at it here, we can say, okay, the best, what's most likely to happen is that both of them won't confess, because clearly looking at this, this is the least bad option, so to say. So you can see here that the utilities are all negative, right? Because going to jail is a bad thing, whether you go for 1 year or 2 years or 5 years or 10 years, it's a bad thing compared to the situation before they were caught, where they were going to go to jail for 0 years, right? And that's why the utilities here are negative. Now, what happens is, so it is, most people will assume, and I did too, that the best strategy was for both of them not to confess, because clearly both of them only get 2 years in jail. And because neither of them has confessed, they're like still friends and stuff, right? Can anyone tell me whether or not this is the correct strategy?
There would be the chance that the other guy does not, does not confess, and in that case, if you confess, then you get like 1 less year in jail. So that way, it is not the best strategy.
Exactly. So what we're going to do is, suppose we're going to fix whatever player 2 is going to do and consider what options player 1 has left. So suppose we fix that player 2 has not confessed, right? So his utilities become irrelevant here. What we're going to look at is player 1's options. Player 1 has either -2 utility or -1 utility. So if player 2 doesn't confess, player 1 has more utility by confessing. So in this case, player 1 will want to confess. Now, if we assume that player 2 confesses, again look at it. The player 1's utility is either -10 or -5. Obviously, he'll want to maximize this utility as well, which is why he'll choose to confess in this case as well. So as you can see, irrespective of the decision that player 2 makes, player 1 is always better off confessing than not confessing. And symmetrically, if we fix player 2's decision here, now we have a utility of -2 for player 2 if player 2 also does not confess, but -1 if they do. So obviously now prisoner 2 is going to confess and say, okay, I'm going to maximize my own utility. I'm going to confess and get only 1 year of jail time. I don't care about the other guy, right? Because we've discussed the players being rational, they're selfish, and they kind of want what's good for them, right? Again, if we fix and say, okay, assume that player 1 has confessed, then the possible utilities for player 2 are -10 and -5. And so obviously player 2 will choose to go to jail only for 5 years over 10 years. Again, they're better off confessing. And so ironically, what happens is that both of them end up confessing and both of them go to jail for 5 years each. So does that make sense to everyone?
Yeah, Shriya, I just have one doubt.
Yeah,
Like every player one can think what player two is going to like play the move, right? So player one knows that player two will be confessing because that's a rational choice. So if
right.
and player two will be knowing the same that they both are confessing, right? So they both could like actually think based on the other person that if they both don't confess, they're facing like the least chance because the other person will also like not want to in that case like minus two situation they can like try to go for that.
Right. That's why usually in real life, if you're like really good friends with your co-robber, people will usually go for this. But here we're assuming that these people are just selfish and greedy. They don't care about the other person. That's the assumption that we're making when we say that the players are rational. So when they're rational, it means that they're going to pick the best outcome for them, no matter what the other person plays. So in this case, this is not confessing is only good if the other person also doesn't confess. But there's no guarantee that the other person also won't confess, right? So in that case, it's always they assume the worst case scenario, so to say, and they say, okay, if I confess, I'm still better off in either case if I confess than if I don't. Does that make sense?
Yeah, it makes sense, thank you.
Cool. Uh, so that was the prisoner's dilemma. If anyone else has any more questions before I move on to the next problem. All right, seeing none, we move on to the Bach or Stravinsky game. So this is a game where there are two players, again A and B, and the strategies, two players, 1 and 2, and the strategies here, A and B, are activities that they could do together. So it's similar to a IISc MG Road example, where player 1 prefers to do activity A and player 2 prefers to do activity B, but they definitely want to spend time with each other. So in this case, you can see that the utility, if both of them pick activity A, then player 1 derives utility of 2 and player 2 derives utility of only 1. Because here player 1 is getting to do the activity they like and they're spending time with player 2. So you get 2 utility. And player 2 here is doing an activity they may not like as much, but they're still getting to spend time with player A, player 1, and so they get a utility of 1. Similarly, symmetrically, if both of them choose activity B, then again player 2 will have the higher utility here because it's an activity of their liking, and player 1 will have less of a utility but still positive. And the utilities are 0 if both of them choose different activities, because the entire objective for this is for them to spend time together. If they choose different activities, they don't spend time together. So this is the Bach or Stravinsky game. If you look at it, we can't really use the same like prisoner's dilemma logic over here, because if you fix player 2 to say that they've picked activity A, then player 1 is better off picking activity A. And we fix and say player 2 picks activity B, then player 1 is better off picking activity B. So the better activity for player 1 changes depending on what the activity for player 2 is. And so in this, it's a truly sort of random distribution whether player 1 will want to, whoever is sort of say more selfish in this scenario will probably win out, right? If player A picks their own activity and player 2 out of consideration picks activity A, then they get to go together. If one of these people is sort of nice and like let's go, then they get to do the same activity and they derive positive utility. If both of them are extremely selfish and only want to do their own activity, then both of them derive zero utility from this, right? And ironically, if both of them also compromise too much and pick the other person's activity, that's also a problem, right? And so in this case, it's always good to have one player who doesn't compromise and the other player who does in terms of their activity of preference. But that, remember, that player is not compromising their utility. So when we say rational, we mean that the players don't want to compromise on their utility, right? But they may be willing to say compromise on their preference and strategy in order to gain more utility. So did everyone understand that? Are there any questions?
So, like in this case, the strategy set for each of the two players is same, but the utility corresponding to the strategy set is different, right?
Yeah, exactly. Exactly.
Okay.
Okay.
Like I had a doubt as well.
Yeah, go ahead.
Like considering like like the assumption that we make for like these games is that both of them should be equally selfish or like equally I don't know, rational, right? So in that case, like, how is it possible for them to reach like a situation where it's not 0, 0?
Right. So I told you that they're rational in terms of maximizing their utility, not choosing their strategy, right? Which means that if if player 2 knows that player 1 is extremely adamant and stubborn and will only choose activity A, then player 2 knows that they can maximize their utility by choosing activity A even though it's not their favorite activity, because the alternative is zero utility. So here you're trying to maximize utility, you're trying to get the best utility. It may not necessarily be your most favored strategy, but what matters here is to maximize the utility. Does that make sense?
If
All right, yeah, got it.
yeah, I have a question here.
Yeah.
If player 1 and 2, they don't know the nature of each other, so in that case they're gonna assume that the other guy is selfish, the other guy wants the better result for themselves. So in that case it would be a given that it is gonna end with 0, 0, 0, the utility.
Yeah, that can happen
Yep.
as well. So what happens in game theory is, okay, so what happened in Prisoner's Dilemma is we were able to get a definite strategy because the utility was always greater for a particular strategy irrespective of the other person's strategy, right? So confessing was always going to give us a higher utility than not confessing for any strategy that player 2 has. But here that's not the case, which is why it's left up to chance as well in some sort of sense. So it also depends on how well the players know each other. It depends on a lot of external factors as well in this particular game.
Yeah, got it. Thanks.
Okay, any other questions? Okay, I'll move on to the last one. I won't discuss this much because this is, I think, a very obvious example. All of us know what it is. We've all played rock, paper, scissors. The interesting thing that you need to note here is that it's a zero-sum game, which means the sum of utilities for each player in each case, right, is zero, which means one player's loss is exactly equal to the other player's gain. So this is what a zero-sum game is. When the utilities in a particular box add up to zero, that's what we call a zero-sum game. So rock, paper, scissors is an example where if you play the same thing, then both players, no one loses, no one wins, it's a draw. So you gain there's a utility of zero for both players. In all the other cases, one person wins, the other person loses. So utility will be negative and positive respectively, and by the same amount, right? Because if you play multiple rounds, say, there's no sort of, it's equally likely and it's equally beneficial to play any of these strategies, right? So that's why you have unit gain or unit loss in each of these utilities here. Does anyone have a question? Obviously, we all know there's no strategy as such to win rock, paper, scissors because this table is pretty much symmetric, as you can see. There's no sort of way you can fix this and like come up with what strategy you can use, because ultimately what you choose is random, what the other person also chooses is going to be random. So yeah. Does anyone have any questions here?
What is meant by zero here? I mean, it is assigned to at least one player in all three cases. So, what does that mean?
Right. So if both the players play the same thing, so if I play rock and you also play rock, then no one wins, no one loses, right? We played the same thing. It's a draw. So both of us, there's zero utility. Neither of us gains anything or loses anything. But suppose you play rock and suppose you play paper and I play rock, right? So paper defeats rock, which means that I lose that round. I get -1 docked off my points or whatever, and you get +1 points. You can look at it that way. And if I play rock and you play scissors, now rock defeats scissors, so I get +1 points and you lose 1 point, right? So that's how this payoff matrix is constructed. Was that the question?
Yes, that was something that I have doubt. I have that same doubt.
Okay, is it clear now?
Yeah.
Okay. So these were the three payoff matrices we discussed. They were all different. So in this case, all the utilities were negative, which means you're trying to pick the best out of all the evil options that you have. In this case, all the utilities were non-negative, which means you're never going to be worse off than you were earlier, but ideally you want to be better off than you were. And here it's a zero-sum game where it's anyone's game. Anyone can choose any sort of strategy, and you can either win, lose. There's no guarantee of whether you're always going to be at least better off or whether you're at least never going to be worse off. It's anyone's game in this particular example. So those are the three payoff matrices. Now we come to an interesting problem called the tragedy of commons, right? And this happens everywhere around us. There are a particular finite amount of resources, and obviously being selfish individuals, we want as much of that resource for ourselves as we can. But because we live in a society, we have to share those resources, and we also need to get along with other people. So there's a trade-off between how much you can sort of take for yourself and how much you can let go of in favor of your social interests and your social well-being, right? And so the example we'll take here are the village has n farmers. So that set n originally is 1 to n, and the strategy set of the individual farmer is 0, 1. So 0 if they keep one sheep, if they don't keep any sheep, and 1 if they keep one sheep. Here we're assuming that the farmer unfortunately does not have money to buy more than one sheep. So they either can choose not to buy any sheep or they can choose to buy one sheep, right? And so the strategy sets are equal for all the farmers in this case, just like we had seen in the ISCMG road example earlier. So it's 0, 1. Those are the strategy sets for each farmer. Or does anyone have a doubt in this slide? Okay, I'll move on. So now we're going to look at the utility that you get, right? So if you have a sheep, then you'll get some sort of milk, wool, you'll get stuff from that sheep, right? And so you can say that the utility from that is 1 unit. So you get some positive utility. But what happens is the village around has only a limited amount of grassland, right? And so when the sheep goes and grazes on this grass, there's the damage to the environment. There's all that soil erosion stuff that we studied in EVS and geography and all that. And so whatever that gives you -5 utility, right? Which means you're losing 5 units of utility. And this damage to the environment is going to be shared equally by all the farmers. So what happens? So now I've written, this is the equation for that utility. So this is utility I. So the utility for farmer I, given the strategies of the n farmers, is the strategy of that farmer minus 5 by n. So 1 in, you can say it's 1 here. So let me just, so 1 into SI, because, yeah, just 1 minute. Yeah, plus 1 into SI because they gain 1 unit utility, minus 5 because they're losing 5 units of utility because of the damage to the environment, minus 5 into the sum of the strategies. So see that if all the farmers choose to keep sheep, then this will be minus 5n divided by n, right? If none of the farmers choose to keep any sheep, then all these strategies will be 0. And so this damage to the environment will be 0, right? And so this is how we represent the equation. So SI minus 5 into the damage by the environment, and is divided by n because it's going to be shared equally by all the farmers. So this is how the utility equation is for this particular case. And let's just look at the payoff matrix. If there are 2 farmers, and neither of them keeps a sheep, they don't gain anything, they don't lose anything, so the utility is 0. If both of them keep a sheep, then what happens is SI will be 1 for both of them, 5 into 1 plus 1, so 5 into 1 plus 1 divided by 2, which will give you minus 5, right? So 1 minus 5 is 4. So both of them have minus 4 utility. Now what happens? Suppose farmer 1 decides to keep a sheep and farmer 2 doesn't want to keep a sheep. So first we'll calculate the environmental damage, right? So it will be 1 plus 0 divided by 2, which will become minus 2.5 now. In this case, the environmental damage for each farmer. Since farmer 1 is keeping a sheep, their utility will be 1 minus this, because they have that SI, that utility of having kept the sheep. So 1 minus 2.5, they get minus 1.5 utility. The second farmer hasn't kept a sheep, So even though they don't have a sheep, they're still sharing this environment damage. So their utility is minus 2.5. So you can see here, if farmer 1 doesn't keep a sheep and farmer 2 does, farmer 1 has minus 2.5 utility, farmer 1 has minus 1.5 utility. If farmer 1 keeps a sheep and farmer 2 doesn't, again the utilities are reversed, right? And if you construct the payoff matrices, you will see that if n is less than 5, then the farmer gets less utility by keeping a sheep than not having one, right? Again, we can look at it the prisoner's dilemma way and say, okay, suppose farmer 2 has not kept a sheep. This guy is better off not keeping a sheep because otherwise his utility will become 0. Suppose farmer 2 has kept a sheep. If this guy also keeps a sheep, then his utility will be less than if he does not. So player 1 will prefer not to keep a sheep, and symmetrically player 2 will also prefer not to keep a sheep. So in this case, if n is less than 5, then the farmer gets less utility by keeping the sheep. If n is equal to 5, then there's a sort of equilibrium reached, and whether or not you keep a sheep becomes irrelevant. You'll have the same amount of utility. And if it's greater than 5, the farmer will gain more utility. And why we're using 5 here is because the damage to the environment is 5 times the damage, the utility of keeping a sheep. So if this was equal to 10 units, then this equation here would have had 10. And here n greater than 10, farmer would have gained more utility. N less than 10, farmer would have got less utility. N equal to 10, farmer could be indifferent. So that's how this works. Does anyone have any doubts up until here?
How will one gain the utility by not keeping the ship? I mean, if not giving him the ship, then how will it give him any reward or any kind of positive output?
Okay, so we've seen that. So we're going to fix. Suppose we don't know what farmer 1 doesn't know what farmer 2 is going to do, right? So suppose we fix and say, okay, in case farmer 1 doesn't choose to keep a sheep, now the possible utilities for farmer 1 are minus 1.5 and 0, right? If farmer 2 does not keep a sheep, then the possible utilities are minus 1.5 and 0. Now 0 is greater than minus 1.5, right? And so by not keeping a sheep, farmer 1 is maximizing their utility. Similarly, if we assume that farmer 1 has kept a sheep, now you can see the possible utilities for farmer 1 are minus 2.5 and minus 4. And this is greater than this, right? Obviously, just give me a minute. Yeah. So this is greater than this, right? Obviously, farmer 2 will want to maximize their utility. And so even if farmer 2 gets a sheep, farmer 1 will not get a sheep. Because if farmer 1 also gets a sheep, then they'll have minus 4 utility, which is bad, right? Compared to minus 2.5. So symmetrically, you can fix the options that farmer 1 has and see which option will give more utility for farmer 2. Does that make sense?
Yeah, okay, now understandable.
Okay. So now we'll come to a slight modification of this problem and say, okay, now the government is like, no, environmental pollution is very bad. So we're going to levy a tax. All right. So they give a pollution tax of 5 units to every farmer. So now the payoff here, we're just going to add minus 5 SI, which means that if they keep a sheep, then the tax is 5 units. And if they don't keep a sheep, it's 0 anyway. So in this case, you can see SI minus 5 SI is minus 4 SI. So in this case, the utility will always be negative because this quantity is negative, this quantity is negative. And so no matter how many sheep the farmer gets, they're never going to get beyond a point where, okay, if say 20 farmers keep a sheep, then somehow maybe the utility will be positive for them, right? That's never going to happen. And so it's always going to be negative. So none of the farmers will buy any sheep if there is any sort of tax. Even if this tax is just 1 unit, if the tax is even equal to the utility of keeping a sheep, then this quantity will become 0 and this remaining quantity is still negative. So even then the farmers will prefer not to keep a sheep. Only if the utility of the tax is less than the utility of 1 unit, which is from keeping the sheep, only then will the farmer derive some sort of positive utility beyond a certain number of farmers. And so that's why this tax modification is pretty interesting to look at. Is there any question? All right. Seeing none. Yeah, did you have a question? Okay. So we'll come to the last topic that we're going to discuss today, which is called the best response strategy, which we've been discussing this entire time. This is just a formal statement for it. I can share the slides with you later on, and the recording is also available, so you can go through this definition. But I'm just going to explain it in simple terms. Basically, if UI is a particular strategy, is the utility derived from the strategy SI, and SI dash is any other possible strategy that that player can take. If SI is the best possible strategy for that player, then the utility derived from SI will always be greater than or equal to the utility derived from SI dash, which is any other strategy that that player can take, right? So this basically, it's just the mathematical way of writing. The best possible strategy is always better than or at least equal to any other possible strategy that the player can take. So does that make sense? And a strategy profile S minus I here means the strategies of all the other players without that particular ith player strategy. So if we have 1, 2, 3, 4, 5 players, U1 of S1, comma, and S minus I will be 2, 3, 4, 5. So excluding 1. That's what this S minus I means. The strategy of all the other players excluding the ith player. So does this definition make sense? You can take some time and read it, but that's what the basic statement means. Any questions? All right. That's the last topic we had. Thank you for tuning in, guys. I really enjoyed giving this talk. And please do come. I think 2 weeks from now, we'll have the second talk on Nash equilibrium, etc. And that's also going to be really exciting. So I really hope you guys tune in. Thank you so much. And if there are any questions, I'm happy to take them.